Edexcel Core Pure, second order differential equations 3, modelling with second order differential equations. 3.3 Damped oscillations, plotting and interpreting solutions. So we're starting to look at this damped oscillation equation in a little bit more detail. So it's second order, it's linear, it's homogeneous, but we now have the coefficients k and omega squared. So this is similar to the situation we've seen that produces simple harmonic motion, where the acceleration and hence the force will be proportional to the displacement. So that's the effect of the first term and the third term. They would produce simple harmonic motion. However, we now have a braking force, if you like, which is proportional to the velocity, dx by dt. So that's this extra term here, which is creating the damping effect. And the bigger the value of k, then the bigger that damping effect will be. So the second order difference equation has an auxiliary equation of the form lambda squared plus k lambda plus omega squared equals 0, where omega squared is the coefficient relating to the simple harmonic motion and k is the coefficient relating to the damping effect or the braking effect. So the nature of the solution we get, and hence the degree of damping that we're going to experience, will depend upon the discriminant k squared minus 4 omega squared. So k squared minus 4 omega squared is the discriminant, and it will determine the different level of damping that we will experience. And we'll have a look at this in a little bit more detail using a GeoGebra file. So at the moment we have omega is 5 and k equals 0, so this is no damping whatsoever because the braking term, the damping term, is 0 due to k. Omega, don't forget, determines the period of the oscillation. So for example, when omega is 5, the period is 2 pi over 5, and we can see that here. Yeah, one complete cycle has a period of 2 pi over omega. So at the moment there's no damping, and if I have a small amount of damping, such as k equals 1, we can see that there is still an oscillating system here, but the amplitude is decaying due to the small amount of damping that is occur. So at the moment this is under damping. We're still getting quite a lot of oscillations that are decaying as t gets bigger and bigger. And as k gets bigger, you can see that the decay happens more rapidly. As k gets 3, 4, we're getting very rapid decay of the system. If we go, for example, to k is something like 15, then the damping effect, or the braking resistive force, if you like, is very strong, and we can see that there's no oscillations occurring whatsoever, and at the moment we have an over-damped system. If I go to k equals 10, however, we have a slightly different situation, which is called critical damping. So now the discriminant is 0, and we have a situation in which we are at the cut-off point, if you like, the boundary between the under-damping, where we get quite a lot of oscillations, decaying oscillations, and over-damping, where the discriminant was positive. So the discriminant is positive when there is over-damping. And when k is less than 10, we have an underdamped system, and at k equals 10, we have what's called critical damping. So to summarise, we have a second order linear homogeneous equation where a, b, c are all positive coefficients. This produces the auxiliary equation a lambda squared plus b lambda plus c equals 0, depending on the coefficients of a, b, c. And the solution to this will be decaying exponentially as t tends to infinity. If we look at this discriminant in a little bit more detail, so if the discriminant is negative, then we have very little damping, and we said it's an underdamped system, and we can see the oscillation slowly decaying away. If the discriminant is positive, Then we have what's called an overdamped system, and the boundary between underdamping and overdamping is when the discriminant is 0, and we call it critical damping. So for example, if you're talking about an old car where the suspension's worn, if you push down on the corner of an old car, it's likely to bounce up and down quite a bit, and the damaged suspension has produced an underdamping effect. If you look at something more like a sports car, where you don't want the car to bounce around so much, then you would have a discriminant that's positive, and you would have an overdamped system. The other thing to notice is graphically, it's quite difficult to tell the difference between an overdamped system and a critical damped system. They look graphically very similar, although we know that if it's overdamped, the discriminant will be positive, so that algebraically we know whether it's overdamped, and critical damping is when the discriminant is 0. In the next video, we're going to be looking at solving simultaneous differential equations.